Today we're going to look at composite figures. There are two postulates which pertain to today's lesson. First, if two polygons are congruent, then they have the same area. Secondly, the area addition postulate. The area of a region is equal to the sum of the area of its non-overlapping parts. So in the case of the polygon shown, the area of the entire polygon is equal to the area of the three smaller parts, which are non-overlapping. So we're going to apply that area addition postulate right here with this example. We've divided this irregular hexagon into three parts. There's two triangles and there's a rectangle. Let's start with the triangle on the left. Using the formula half of the base times the height, recognizing that the base is 8.5 inches, the area is 17 square inches. In the rectangle in the middle, we're going to use base times height, and the area is 51 square inches. Now the triangle on the right has three sides that are congruent to the triangle on the left. Therefore, we're going to understand that they are congruent and their areas will be the same. Now we're going to add these three parts together, and we get 85 square inches as the area of that irregular hexagon. So here we have an example. We're asked to find the area of the shaded region. And it's not exactly convenient to split this shaded region into parts and then add them together. But what is clear, what is hopefully an efficient strategy, is we're going to find the area of the outside rectangle by using base times height. Then we're going to find the area of that unshaded triangle, half of the base times the height. It's 132 square millimeters. Now we're not going to add these things together. Instead, we're going to realize this, that 390 is really represented by the area of the blue plus the 132. So now we're going to do a subtraction problem to find the area of the shaded region. So you'll see sometimes it's more efficient to add parts together when you're finding the area of a composite figure. Other times subtraction will be the better approach. Okay, so this is a swimming pool, and there's tile that's surrounding the swimming pool. And we're asked to find how much tile is needed. So this is actually a perimeter problem, right? So what we're going to do is we're going to understand that those two pieces which indent, we could actually bring out and up. Same thing with the bottom right corner. We could slide it, the vertical piece over, and slide the horizontal piece down. And then we can just find the area of that outer rectangle now, which is the 25 plus 40, right, plus 50, etc. We're going to get 350 yards. So the bottom of the pool is covered with concrete, and if we're asked to find how much concrete is needed, now the question comes up, is it better to divide this into separate parts and add them together, or should I do a subtraction approach? Well, it's pretty clear now if we were to look at this as like finding the area of the outer rectangle. The base is 100 yards, do you see that? Because you're adding the 60 and 40 together. And the height is 75 yards. So finding the area of that outer rectangle would be pretty easy. Then we can just subtract off the area of the two corner rectangles, which turn out that they are actually congruent. So that's going to be our approach. 7,500 square yards is the area of the outer rectangle. And we'll multiply 40 by 25 to get 1,000 square yards for each corner rectangle. But remember, there's two of them, so there's really 2,000 square yards we'll be subtracting off. And our final answer is 5,500 square yards of concrete are needed. So here are a couple of nice challenge problems. What I would recommend that you do is to put this video on pause. Give them both a try. I would encourage you to look at the structure of the problem. One of them, adding like splitting the figure up into separate parts and adding those areas is probably a more efficient strategy, and the other one, a subtraction approach, might be the more efficient way to go. So go ahead, put it on pause, and then we'll come back and check. So here I've divided this figure, this pentagon, into 3 parts. A left triangle, a right triangle, and a middle trapezoid. So the area of the triangle on the left is 5 square units. The area of the trapezoid, using half of the height times the sum of the bases, is going to be 8 square units. And the area of the triangle on the right is 1.5 square units. So what I'm going to do is I'm going to add those pieces together, and I'll get 14.5 square units. How did you do? And did you divide it up the same way that I did? I'm just curious. You could have solved this another way. Now the figure on the right, I decided to look at that as a subtraction problem. First of all, I saw that outer rectangle, which is 20 square units, and I noticed that the vertices of that shaded triangle hit what we call lattice points on the grid. So it would be very convenient to find the area of those 3 unshaded triangles. So the unshaded triangle on the left is 4 square units. That top right rectangle has an area of 5 square units. And the bottom right has an area of 3 square units. So to find the area of the shaded part, I'm going to do the outer area, 20, minus the sum of those 3 unshaded triangles. Remembering I have to use order of operations, right? And add those together first. I get 8 square units as the area of that the area of that shaded triangle. So let's summarize what we've learned. There's 2 main approaches when you have composite figures and you're finding the area. One, you could split it into different parts and add the parts together. And 2, you could find the area of the outside region if it's convenient and subtract off the unshaded or the inappropriate areas. And you know what? In order to know which of these approaches is better, you really want to look at the structure of a problem and just kind of go for that approach that you think would be most direct. So for these 2 examples, remember we used the top approach for the figure on the left, and we used a subtraction approach for the figure on the right.